Good morning. Good morning. Let me send the link in case people haven't sorted out how to get here. All right, some people are here. Good morning. Good morning. Okay, so share the link if people are having trouble, but you should usually go to the playlist, the MBA UNDH live playlist, and you will find the lecture live stream there. I'm going to send the link to everybody again, but it's usually the same thing. It will be the same thing. How was your evening? Did you have any time to look at the materials? I understand that Taylor is going to be available to work with you. I have to send him the notes as well. So I just sent you the solutions to the exercises that I shared with you yesterday, and some documents for today. Alain Sauveur, Marcel. I have to admit, I can't tell very well which are the first and which is the second name of many students. So excuse me if I get it wrong. I want to say your whole name. Okay, people are coming. So I'm going to, hello Alex, Samuel. So what I'm going to do is pick up where I left off, take a moment to look at the review exercise solutions, but you can work with those work on those with Taylor later today. Hello, Francette. Luxo. Bonjour. Good morning. How's the sound? How is the sound today? Very good. Hello, Anouk. Okay. All right, so let's see. We have 10 people. It's already 10 minutes past 9. So I said, let's just look at where we left off. So we solved several problems, and introducing you to applying time value of money. I put a couple of tips at the end of the notes regarding counting. Now, we all think we know how to count, but with this time horizon, with the timeline, you have to be careful that you understand the difference between counting intervals and counting payments that occur at end or beginning of periods. So for example, if I ask you, how many intervals are there between 55 and 18? So this is period 18, and there's many periods between to arrive at 55. How many intervals are there in between those? And this is important because let's say growth of growth has to be added, or some sort of indexing, let's say, occurs to payments, so they have to grow steadily over a certain period at a fixed rate. Then I need to know how many growth periods there are. So how many intervals are there? Well, it's just 55 minus 18, correct? So if you ever get stuck, I suggest, look at your hand. So you could say this is 1, 2, 3, 4, 5. And when we talk about intervals, what we're discussing, good morning, Harry. What we're discussing is the intervals between. Think about the fingers as these marks, these larger marks, tick marks. The intervals are between. So between 1 and 5, you would calculate 5 minus 1 and see there are 4 intervals. So similarly, there are 37 intervals between 55 or 18 and 55. So to figure that out, in general, use this principle to count the number of intervals. Start at the end of the last period minus the end of the first. So if you went from 18 to 55, this would be your end, and this would be the end of last. This is the last period. Dernier. And this is the first period. I think that's, anyway. So that's the way we calculate. What if instead we talked about beginning? You saw a question with beginning. You can use the same approach This would be called the 50, you would refer to this as the beginning of the 19th period. And this one would be the beginning of the 56th period. So if you worked with beginning, referring to this as the beginning of the period, and this position as the beginning of 56, so this would be beginning of 19, beginning of 56, you still use the same rule and you get the same answer. If you subtract 56 by 19, you'd also get 37. So I'll make a note. Okay, so you might find that useful if you have to figure out how many intervals there are. What if you have to sort out how many payments there are? So let's see how many payments are there between the beginning of the 19th, which is really 18, and the end of the 55th, which is 55. So we have to realize, first of all, this is the 19th, and it's marked by the end of the 18th. So putting together the end of the 18th you want to sort out how many payments would be between if you had to include 18 and 55. Again, look at your hand. All right. 1, 2, 3. So if you think of your fingers as the payments, as the larger tick marks as we did before, now you see there are there's 5 fingers, right? Of course. So 5 fingers. How would we calculate that? If we subtract 5 minus 1, we know we only get 4. So in fact, you have to add 1 back. So you need to remember this. If you are counting payments, you have to add 1 back. So to figure out how many payments between 18 and 55, if there's a payment, if there's a cash flow, at every point, good morning, Evelyn and Michael. Okay, so you want to count all of these cash flows, how many there are. So you would have to take 5, which is the end, minus 1, and then add 1 back. Okay? So here it's 55 minus 18 and add 1 back. So there are 38 payments in between here because you can't see otherwise how many there are. Any questions? So you might not see this immediately, but there might be problems where you'll need to figure out how many there are. Okay. So now that we have half of the students, 15, let's get into some of the review exercises. I just want to point out we did this one yesterday. So we did this together yesterday. What I expect from you again is that you express the formula with the values and then the solution. That's sufficient for this question to get full points. So here, I'm just really going to just show it to you because I'm going to ask Taylor to work with you on this. Did anybody try these problems and have difficulty with any of them? Let's do this one together. Let's look at a mortgage. I'm going to take the question. Oops. Let's do this one together. That's not what I want to happen. Okay, let's look at this question. This is number 4, I think. So a couple, good morning. The couple requires $100,000 in mortgage financing. So that means they are looking at purchasing a home and they want to borrow $100,000. And banks offer these types of loans given a person meets certain criteria and they have a good credit rating, good history with borrowing money, and they figure out that their effective monthly interest rate, because mortgage payments you have to pay for the loan, are effective monthly. The mortgage interest is effective monthly with 1%, and we're going to discuss more about what effective means today. Calculate the monthly payment that they can expect to pay if they accept a mortgage with a 20-year term. Okay, let me give you some minutes. Work on this for a few minutes. And then I'll work on it with you. So if you did not get my email, please let me know. I will send you the documents. Possibly my emails are going into spam mail. There are a few students that aren't receiving my emails. Check that, verify, because it looks like they're going through. I'm not getting any reports that they are not going through. Okay, so this is question number 4 on the document number 3. So what formula would you use for this? Good morning, Jeffte. Oh no, where's Jeffte? Jean-Baptiste. Edmond. Good morning. I don't see Jeffte. Oh, there he is. Yes, good morning. Okay, So what formula would you use here? So looking at our formula sheet, let's pull it up with a summary of the formula. So which one of these should we use? Which one of these should you use? Comments? Anyone? Which formula should we use? All right, no comments. Okay. So you need to use the annuity formula. The annuity formula, because this is a mortgage payment is a loan. And I'm going to do this in months so that there are 20 years the number of payments is 12 months per year times 20 years. So there's a total of 240 payments. There are a total of 240 payments. And good morning. The interest rate is I equals to 1%. With 240 payments, what's missing? So let's write down the formula for an annuity. PV0 equals C1 divided by I, 1 minus 1 over 1 plus I, with the power of T. So I is 1%. The C1 is what we want to find. The C1 would be here. Every period you have to make a loan payment. So it looks like an annuity till the end of 240 payments. So that's just an annuity. It's regular installments like that. T is 240, and PV0 is the loan. That's the principal amount that's borrowed. We're going to talk more about loans, mortgages today as well, so this is just an introduction. So let's put all the values in the formula and then use our calculator to solve it. So we put in $100,000 and then C1 is what we want. We put 0.01 for the interest rate and then 1.01 to the power of 240. That's the formula that we need. And next, I honestly don't understand why things get separated. Okay, so in your calculator, to get this, well, mathematically you could solve this. If I solve this mathematically, I should put all of this together in my calculator and then divide 100,000 by this amount to find C1. Or let's just use our finance calculator. From left to right, 240 into N, 1 into interest, 100,000 into PV, and we're receiving that, so it's a positive. And then payment is what we want to find. And there's nothing in face value or future value. We're interested in PV. We only use all of the keys when we deal with bonds, right? Otherwise, we have to pick either if we want the future or the present value. And compute payment, what do you get? So someone gave me a number. I don't know. That is not correct. That's too much, right? What is the payment? They have to make 240 payments to pay back the $100,000. So what's the size of the payment? Tell me the answer. is 100,000. Aha, Anouk got an answer. Let's see, can somebody confirm the answer? Oh, Harry, yeah, no, it's a positive. I put it here already. So the payment will show up negative because that's what you have to pay. To get 100,000, you have to pay it back with interest of 1% a month. So as the loan remains unpaid, you continue to accumulate interest. We're going to conduct an amortization today, so you'll see how that works. So let's see, I'm going to do this on my calculator. So 240 is N, interest is 1, the payment, the principal amount, the amount borrowed is 100,000, and I have to put 0 into future value because I'm not interested in the present value, working with the present value, not the future value. And you ask to compute payment, and you get this, and Anouk is right. Very good. And Harry is right, and Diego is right. It's okay if you're late, but you just have to catch up now. So all we've done is one exercise together, and Taylor is committed to work with you on the other exercises. I hope everything is all right, by the way. My father mentioned to me yesterday that your Prime Minister has stepped down, and I hope everybody's safe. And what can I say? I'm hoping for the best, for a better leadership. We all want better leadership. Okay. So 101.09 is the answer. So you finish, you solve the problem, circle or box the answer, and that's it. Even though it was returned in your calculator as a negative, that just means that it is denoting you have to make a payment to receive the 100,000 today. Okay, anyone have difficulty? So this is useful, right? So you can figure out if you want to change your payment. If you want to change your payment or you want a lower payment, then you have to see what you can do, right? What could change? You could, if you want a lower payment, maybe you have to make it a longer term, or maybe the interest rate has to, I don't know if you can do that, but maybe a longer term. The interest rate here is determined by the bank, and obviously the customer should shop around to different banks to find the best interest rate. Right now, interest rates are low in the United States and Canada. I'm not sure in Haiti, but they're very low. All right. Did you get the answer? Can you hear me? Why 100,000 plus? Because it's plus 100,000. First of all, because that is the amount of the loan. This is a loan, right? A mortgage is a loan. This is the principal. Or present value. And you receive it. If you receive it, it's a positive. Yeah, this is a simple one. This is a simple problem. We're going to get more complex. Trust me. I don't want to get too complex. Okay. All right. Harry? Shao? Is that all right? All right, so that's a simple one. So the other thing, if you want to solve it analytically, you can, but you don't have to. You have your finance calculator, okay? So that's it. That's all you have to do. So this has this set of exercises. There were how many? 6 problems. There were 6 problems. Okay, so you can work with those with Taylor on those. And then there was another exercise I gave you for annuities, and we did these already. So these are just the formal solutions with all the steps. So we did this yesterday. The last one is provided here. So I'm going to ask you to practice this. This was handout on annuities, handout 4. These are the solutions I just sent you for 4.5. And this question here about solving this, the value of this set of cash flows. And again, this could be done using the cash flow keys of your calculator, but what I wanted you to do is use annuities. So you need to practice using the annuity formula. Okay, so I leave that to Taylor, unless you have direct questions. Otherwise, I want to move to the next related topic. I'm going to start here on, okay, this is document 8. This is document 8. Okay, so have you got it? Let's try this one. So by now, what you should have, if you have your documents, I don't know how you're working with your documents, but at the very least, print the formula document. I mean, I recommend print them all. But if that's not easy to do, just print the formulas document and have that nearby, because that summarizes everything you need. Okay, and add formulas as you go along. Good morning, Natalie. So try this problem. So this is document 8. So what will $150,000 be worth in 20 years if the annual effective interest rate is 15% for 10 years and then 8% for the remaining? That didn't work. Do that again. So this is a timeline in years. And for the first 20 years, no, sorry, that's not 20. In the first 10, I'm going to do this. In the first 10, there's a 15% interest rate. In the last 10, there's an 8% interest rate. How do you solve this? Which formula do you use? Any comments? So how will you handle this? You'll take the 150,000 here, and then it will accumulate to, let me know if this is a bad color. It'll accumulate to 1.15 for 10 periods. This is the basic time value of money formula. So you have accumulation for 10 periods. So there's in here, there's 10 intervals of interest. And then it will begin accumulating at 8%. So you have to modify. So what I'm doing right now is modifying the approach. I'm applying the formula, but then it has to be applied again. Okay, so I repeat. I continue accumulating this amount, but now a new interest rate. So that's not hard, right? Is that an okay color? Maybe green is not the best color. And you can put this in your calculator using ten into n, and then (15) into I, and 150. You're putting it into an investment or savings, so that's out of your pocket. That would be a negative, into PV. And then there are no payments, 0 in payment, because this is just a lump sum that accumulates. And then 0 into FV. Oh no, sorry, we want to compute FV, sorry. You want to compute FV. And then that amount, you want to accumulate it some more. Whatever that amount is right here, then you want to take 10 more years. Not plus, Samuel. Nope, it has to be multiplication. It must be multiplication because it has to have the compounding effect. No, it must be multiplication. So let's continue with this. If I did this with my calculator, 150,000, so let's second clear TVM, 10 years of 15% of 150,000 with no payments, this becomes 606,833. Did I do it correctly? Once again, 10 years or 10 periods at 15%. Did I do the, is it 10%? No, I have to remember. 15% for 10 years, 150,000. I did it right. And then 150,000 and no payments, compute. So that is the future value up until that moment. I will change the sign. Now this amount I want this amount to become the PV because I want to continue accumulating. So I'm going to put that into the PV. Again, from beginning, from left to right, I want 10 more years, now 8%, with the PV that I entered, 0 payments, now compute FV. And that is the final answer. So this is why these are not so challenging, but they're important that you clarify some things before we get to the challenging problems, okay? So for this one, shall I do it again? Let's do it again. So second clear. Once again, 10 periods. It is 15% for a $150,000 investment, no payment, and I asked to compute the future value. So that's 606,833.66. So what I'm going to do just to keep track is put that in on this document. Just as a note, but you shouldn't round, you shouldn't do anything but write that number. One moment. So 606,833.66. So and you don't want to round it. You want to keep all the decimal places. This is why I immediately put it into the principal amount. So this is like the new PV. And then I accumulate it for another 10 periods at 8%. So I change the sign, I put that into PV to store it. I could also put it in storage here, storage 1, as a backup. And then for 10 periods at 8% with that present value amount and no payments, I get the total value of $1,310,108.36. And that's my final answer. Take a screenshot if you want. I'm going to go and write it here. So the final answer, so just to recap, this was, the first part would have been, but then we have to do this again. Make sure you change the sign. It will come as a negative, but you have to change it to a positive. Or you can, well, it can be a negative. You can put it in as a negative. That's fine too, actually. I don't need to change it. You have to keep track, don't get confused by the positive and negative. It's just for the calculator to keep track of the inflows and the outflows for you. If you don't enter it properly, you're not going to interpret it properly. So that's PV, 0 into payment. And then I ask for compute future value. And the final amount What is happening? This didn't go along. Oh, sorry. I just want to move this over to make more room. The final answer. I'll put the final answer here. The final answer is future value of 20 is equal to 1,310,108 and 36 cents. Questions about it? It's my final answer, so I will circle it. All right. Any questions? Let's try the next one. Any questions about that? Can I go to the next one? Tell me to slow down if you need me to. Everyone all right? Can I continue? Give me the green light that I continue. Okay. Okay, let's look at this together. Okay, so now in this exercise, we're going to hit an obstacle because we don't have the tools to solve this, and I'll explain why. Okay, you're going to think you can do it, but Well, maybe you can with other tools, but nothing that I've taught you so far. Starting 1 quarter from now, Lydia will begin to deposit $1,000 at the end of each quarter into an account to save for her retirement. She will do this for the next 30 years. How much will Lydia have accumulated at the end of 30 years if the annual effective rate of interest is 5%? Okay, so you want to draw this. And right now my drawing is going to represent quarters. Quarters are 3 months. 3-month periods. So I'm going to make this drawing in terms of quarters, but also I will mark when the year has passed. So okay, so the smaller ones are quarters and the higher ones are years. What I'll do is I'll just write quarters for now. And you can see this is 1 year here. And then, so she's going to deposit $1,000. I'm going to write 1 with a K. Okay, that means 1,000. Oh, maybe that's confusing. I'll fit it in. 1,000. At the end of each quarter, into an account to save for retirement. So she's going to do this repeatedly. And she will do this for the next 30 years. $30 years is how many quarters? The effective annual interest rate is 5%. So how much will Lydia have accumulated at the end of 30 years, if that's the case? So how would you figure this out? What formula should you use? Very good, Alain. So, which formula should we use? Since the payments are ongoing, they're all the same, and the first one is 1 period from today, I could use the annuity formula. And here, C1 would be the 1,000. And 120 would be the years, or sorry, periods. But what would be the I? So we have 120 would go into N. And we don't know what I we should put into interest. The PV is what we'd like to find, or no, we want to get FV, right? So we're going to put 0 into PV because we're interested in FV. We get to trade off and get FV. The payments we know are $1,000, and those are out of pocket for Lydia. So that's a negative. And then we ask for FV. But I'm left with wondering what is the interest rate that I put here. Right, Sévère. Monsieur Sévère. It's annuities. So what is the interest rate that I should put here? This says annual effective rate is 5%. But for this formula to work, the timing of the payments must be the same as the compounding period of interest. So the formula these formulas that I've given you, they require that the timing of the payments matches the compounding period of the interest rate. So timing of payments here are quarterly, but the interest rate is annual. So how do we solve this problem? Okay, so some people have told me you just divide, right? You divide by 4. Oh, let me make this visible. Hold on. One minute. Keep thinking about it. The formula every formula I give you requires that the timing of the payments must be the same as the compounding period of the interest rate. So this is quarterly, and this is now the payment. The payment you can't change. Those are quarterly. You can't change that. So the decision is to change the rate that we're using. But what would be the equivalent rate? This is the question. We are compounding a balanced amount, right? A set of deposits. We are compounding them with interest compounding as well over time. And let's look at that. It is not dividing by 4. So that is what the first thing I have to tell you. It's not just dividing by 4. If I told you, if I said to you that the rate 5% per year is compounded quarterly, in this case, it's stated over the year but compounds quarterly. In this case, all you have to do is divide by 4. But that's not what I gave you. So I better say if. If the rate is 5% per year, notice the terminology, compounded quarterly, then the effective quarterly rate that you can use in the formula, the effective quarterly rate is 5% divided by 4. But that's not what I gave you. I told you that the rate is effective. So what is the difference between effective and this? This is what we're going to discuss now. And then we'll go back and solve some of these problems. And I'll leave the rest to Taylor. No, Monsieur Sever. That's not how you do it. So the multiplication and the division. So you have to think about what you have. This is where we're misunderstanding things. And it's very common that people misunderstand rates. So you have to be clear over what period is the rate being stated and what is the compounding frequency of the rate. This says what I gave you was not the rate 5% per year compounded quarterly. What I gave you was 5% per year compounded annually. When those statements, the duration over which, or the statement over which, or the period over which the statement is being made, and the compounding frequency, when they match, this is called effective. And I use the notation EAR. So what I gave you is the EAR, the effective annual rate. And you know it's effective annual because these match. In the case above, let me divide. In the case above, we are given the rate per year compounded quarterly. This is a simple interest rate. This is not a compounded or effective rate. It's a simple interest rate. to derive 5%, and you guys were close, to come up with 5%, what was done was the hidden rate was multiplied by 4 to give the 5%. So bear with me. This is what I gave you. And this is what you guys have interpreted it as, but that's not correct. I gave you the effective annual rate. This is called the simple interest rate. Remember simple interest? And this is the effective interest rate. Okay, they're different. So how do we work with what we've been given? So let me say, this is a simple interest rate. So you see here, by dividing by 4, the 1.25, let's see, what does 1.25 represent? Let's go even further. Let me say this one is a simple interest, and this one is the effective interest, which we want to use in our formulas. Okay, so we need to use effective. Effective is going to do this for us. We need effective rate so that the formula uses the rate where the interest is compounding at the same rate or the same time period. Okay, so this one is called the effective interest rate. This one is called the simple interest rate. What is this? What is this called? I just put it here, the effective quarterly rate. So you are presented, if you are presented with a rate like this that is per year compounded quarterly, that's a simple interest rate which you convert by dividing by 4 to get the effective quarterly rate. It's 1.25. Now this one you can use in the formula for quarterly payments. So just to expand a bit, this one is, and I have lots of notes to explain all this, so 1.25 is per quarter compounded quarterly. these align. So this is effective. So you can convert a simple interest rate into an effective rate. Got that? So I can convert by division a simple interest rate into an effective rate. By division. So why am I saying this is simple interest? Because all that was done was 1.25 was multiplied by 4 to get 5%. When you multiply a rate over periods of time, that's just simple interest. You're ignoring the compounding effect. To actually get the compounding effect, you need effective rates. Because effective rates take care of interest and interest on interest. So let me draw some pictures. So let me draw this. So this is over the year, and these are the quarters, right? Q1, Q2, Q3. So if you had (1.25% in this period, and 1.25% in this period, and 1.25% in this period, and 1.25% in this period, and there was $1 invested here, what would it become in 1 year? Harry Charles asks, since the 1,000 is the same each quarter, what about if we consider 4,000 per deposit per year? No, that's not how it's done. You're going to lose. The value. Okay. So let's see if you can answer. But thank you for the suggestion. No. So what do we do? $1 deposited for 4 periods. What does it grow to? It should grow to, according to time value of money, which we've spent the weekend discussing, this should become $1.0125 to the power of 4 times 1. Correct? And how much is that? The point is, it's an exponent that gets you there, not a multiple, not multiplying. You need to have an accumulation factor effect. Not a multiple, not multiplying by 4. It's in the exponents that things happen. So this would be so if I raised, if this was accumulated 1 period, 2 periods, 3 periods, 4 periods using TVM, $1 should become $1.05. Right? So you must be like, oh, well, isn't that 5%? Well, no, what about all these decimal places here? So let's not talk about $1, let's talk about $1,000 and make it $1,000. And now you see the difference. So I was using the $1, but what if it's 1,000? So you see, it's not 5%, it's more. The simple interest, using simple interest, you lose this effect. Again, it's not, it doesn't look like a lot, but banks operate in trillions of dollars, so this has an effect. There is a difference. Okay, it only looks like a $1 difference here, but if I keep increasing, it's quite a bit. All right, so now that I've shown you that, you can go from simple, you have to know what rate you have. So which rate did we get? We had the rate of the effective rate. Now you show me, how will you find the effective quarterly rate to find the answer? What would be the effective quarterly rate for this problem? So I'm told that from over the year, $1 invested would earn 5% per year. And I want to know what it should be. What would be the equivalent rate for a quarter? So I'm going to do the opposite of what I did here. Rather than accumulating, I have to partition. So $1 should grow to $1.05 for 5% over a year, right? The question is, what would be the equivalent rate over here? Keeping in mind that this amount is different from the one that we found over here. The answer is not 1.25. You don't divide. So how do we find it? Whatever the rate is, the equivalent rate should be such that 1 plus the rate to the power of 4 is equal to 1.05. Again, we're not dividing, we have to use the factors. So this is the way you will find the equivalent rate to use in that problem. So what we've done is we've thought about we need what's called an effective periodic rate over a quarter of the year. That's equivalent to the annual effective rate. So this is called the effective periodic rate. So to find the correct rate, you need to solve this equation. So what this is an introduction to interest rate conversions. Okay, this is what we're going to spend the rest of the class discussing, next hour and a half. And then I will leave it for you to work with all the materials I've given you over the week, solving problems like I introduced you to yesterday, but being aware that you need to make interest rate conversions when necessary. So the notation that I use is in terms of fractions of a year. So this is 1/4 of a year. You could also talk about 1/12 of a year for monthly payments, etc. So what I'm going to do is just take this with me back to the problem. Let's do this problem. I'm going to go back, oops, get the question from here. and start fresh. And you can take time to review all that other stuff that I've said. Okay, so we need to match the timing of payments so you need the effective quarterly rate. So we solve this expression to find it. So the effective quarterly rate is the one that solves this expression. Do you need me to show you how to punch that in the calculator? I'm going to store it because I need that. So let me show you how I punch that in the calculator. I use, clear the screen, 1.05 to the exponent 0.25, that's a quarter, equals -1, and then store 1. I'm storing it because I need it for my annuity calculation. So that's basically the first step of this problem. Now I have the drawing. It's 20, right? So we remember it's an annuity. Then the present value, well, let me draw the timeline. So we have her depositing $1,000 at the end of every quarter. It's Q1, Q2, all the way to 30 years or 120 quarter, or no, let me write it the same way, Q120. And I want to know the future value of that. So I'm going to use the annuity formula, but I'm going to get the future value version of it. The annuity formula says that I take 1,000 and I put it over the interest rate. So here you could write I, or I'm going to write down that I'm going to use the quarterly rate, and then 1/1 plus the quarterly rate effective, and that has to be to 120 periods. And is that going to give me the future value? This is just giving me the present value. What I need to do is together
Put the annuity formula together with the basic time value of money formula to accumulate this amount over to 30 years. So I have to use, I can use the 5% for 30 years, or I could write 1 plus EPR 1/4 for 120 periods. All you have to do is write that down, and the calculator will make the adjustments for you using the time value of money keys. So to get this answer in your calculator, all you have to do is put 120 into N, and then recall 1 into your interest rate, and then PV is what we want to find, but not right away, eventually. And then we want to say, oh no, PV is not what we want to find, right? We want to find FE, so we're going to put 0 in PV. And then payment is 1,000, and she's depositing, so we'll put a negative. And then we compute FE, and it does all this stuff for us. It's magic. And what do you get? Let me know if you have any questions. Okay, you can slow me down or tell me where to go back if you need me to. And have no fear, if you didn't understand what I did here with the interest rate conversion, we're going to spend some time on that. The key thing is to remember is that you begin oops, that's not what I wanted to do. You begin by identifying the timing of payments, and you adjust all rates to the time frequency of payments in terms of their compounding. So what do you get? What is your answer? Okay, you got a number. Okay, different numbers. Keep going. Everyone, see if somebody can confirm either of those options. One catch that I made a mistake myself was to let you know that you have to take the value from the stored interest rate and multiply it by 100 before. It needs to be in percent form, okay, to be an interest rate. So make sure you do that. So it's 1.22%. Okay, you haven't got it yet. Keep going. Maybe fix it with this error. So I had to add in multiply by 100. So remember, all of these payments are collapsed into this present value amount, which we take a lump sum, and then we take the present value and then we accumulate it to get the future value. That's what we're more interested in. That's what we need for our computation. So that's what this is for. And you can do it using the effective rate over the year or the effective rate over the quarter. They give the same answer. Anybody? Any other option? Not yet. Keep going. Try again. Aha, you got it. Very good. So that was maybe because of my mistake in not telling you to do this. Very good. So the future value is correctly given to us by Harry Charles. And here it is. And we can finish complete with the final answer rounded to 66 cents. Oh, Monsieur Sever, double check what you did. So if you neglected to multiply by 100, you will get the answer that you got, monsieur. You need to multiply the interest rate by 100 so that it enters as a percentage into the calculator. Okay, let's see, a couple of you get it. Let me know if you've got the answer. And then what I will do is I'm going to go back and discuss interest rate conversions before we continue. Okay, so I'm going to take a little break, a few minutes. You work on that, and when we get back, I'm going to summarize and we're going to go into interest rate conversions. Okay? Okay, let me put this in the calculator to convince you it works. Okay, let's see. So 120 quarters of $1,000 payments. So I'm going to put 120 payments, and I'm going to recall my interest rate and multiply by 100 to make it percentage. So it's 1.22722 into interest. And for present value, I don't want that. I'm looking for the future value. The payment is 1,000 and it's a cash outflow. So then I compute future value, and there's the answer. Okay. Good. Looks like you're getting it. Okay, so let's go now back to a different document. So that document is for you to work on. All the things I give you are for you to review and work on. Where I want to go next is this document here. So this is a formal review of interest rate conversions. So this is my credit card statement, and if you have a credit card, you have a similar, well, maybe it will be written this way or maybe another way, but in the credit card statement, you should have information about the interest rate being charged. So tell me, I have no balance here. There was no balance, so there's no interest charges. The annual interest rate next period will be 18.4% APR. And the daily interest rate next period will be this amount. Now I'm going to ask you, please, to tell me what is the relationship between these two numbers. Done that. Sorry, the screen. I'm trying to move things around. Okay. What is the relationship between these two amounts? The annual periodic rate and the daily rate. Okay, Anouk thinks that the annual rate is the compound rate. But what is the other one? What is the relationship? How mathematically, how do they relate? Which rate is the effective rate? Okay, the daily rate is an effective rate. This is the rate per day compounded daily. We write the effective periodic rate over the day, so it's a fraction of 1 over 365, is 0.050411%, or as a decimal, it's 0.000500411. So you guys are right about that. That's the effective daily rate, because the statement per day aligns with the compounding frequency. This is what's charged over a day. Then what is the other one, and how do they relate? So interest on credit cards is accumulated, compounded every day on outstanding balance, every day. Try that again. Try that again, Harry. Shao. Okay. Okay, so everybody's okay with that. So interest is charged daily. And this credit card company all they have to tell me is the simple interest over the year. So really, every day I am charged 0.050411. I'll make this bigger. I feel like I have too many zeros in there. No, just 1 0. Okay. Okay, so the interest rate being charged is every day this amount for the outstanding balance, all the way to the 365th day. Okay, so it accumulates all through. So what is the effective annual rate in that case? EAR would be equal to 1.000500411 365 minus 1. That would be the effective annual rate, right? Because it has to accumulate for each dollar. This has to compound 365 times. So what is the effective annual rate? So let's do that. 1.000500411. So clear this. 1.000500411 exponent 365 equals minus 1. So the effective annual rate is really this amount, 20196. Let's just copy that over. So it's really 20196%. Is that correct? So if that's the effective annual rate, and this is the effective periodic rate, so we have the effective daily rate here, we have the effective annual rate here. So what in the world is this thing? Very good, Anouk. Thank you. Luke, so the annual rate may be the daily rate times 30 times 12. Yeah, we just used 365. Luke, so 365 days. And we have to accumulate factors. We don't multiply. We accumulate factors, multiplying factors. 1 plus the interest rate, compounding. Okay, so this is an application of the basic time value of money. Right, because the future value time t equals present value 1 plus it. All I've done is let the present value be 1 to figure out what the rate should be. Anyway, that's what I've done here. I've minus the principal off to get the rate. Okay, so the question remains, this is effective, so what is this other thing? Is this effective? I don't see that number related, so how do we get this number? I think someone wrote it. Somebody wrote it somewhere? No. So whenever you see the term APR, you need to find out what is the compounding frequency of the loan or the contract? Okay, what are the arrangements for the compounding frequency of the account? Credit cards are daily. This is effective daily. APR is just a representative of the simple interest. This is the simple interest annually. All they've done to get 18.4 is multiplied the effective daily rate by 365 and reported that. And this ignores the compounding effect of interest on interest and that's enough to accumulate. Because it's daily, these numbers are very different. This is almost 2 percentage points higher that you're really paying. This does not reflect the actual total payment. So if you have a balance that's left remaining in your account for a year, you're paying 20 cents on every dollar, and the APR is just telling you 18.4 on every dollar. So this is not what we work our formulas with. However, we can use this. I'll put this percentage in here. We can use this, the APR. If we divide the APR by 365, we get the daily effective rate, and we can work on things from there. Questions? So you need to know what you've got, what is the compounding frequency, and you need to convert your rate into the rate that aligns with the frequency of timing of payments. That is what's important to you. Any comments? I'm going to open up 5.5 and we're going to review this together. So these are some comments I made. This is document 5.5. Just going to repeat what I said. The annual periodic rate, or APR, indicates the simple interest paid after a year. Simple interest ignores the effect of interest compounding on interest. So this is not really what you pay. It just looks like it's a substitute to help people, or it's supposed to inform the consumer, but the consumer should be aware they have to divide by 365 to get this value. So I use some notation that I'm going to introduce below. I use this notation to distinguish between effective rates, which are compounding rates, and simple interest rates, or stated rates. So I have a variety of names for these things. So I call this a stated rate, and I call this an effective rate. And the stated rate is just the simple interest It just reflects the simple interest. The notation I use, I already showed you, this is the effective period rate for the day. This is the notation to distinguish from it. So these both are daily rates, but this one is the effective one, and this is the simple interest over the year of the daily rate. Converting a stated rate into an effective rate, well, we know all we have to do is divide this amount by 365 to get this one. The other thing to learn how to do is to convert from an effective to an effective rate, because here's the daily effective rate, but what if this was the daily effective rate, but somebody made payments every month? And how does that change? How does that affect your calculations? So you need to know how to convert between rates. And we just did it. We converted from from an annual to a quarterly, so that can be done. So those are the two main things you need to learn how to do before we leave, or review before we leave, because I did already discuss it, but we need some practice, right? So simple interest ignores the effect of interest compounding on interest. In simple interest terms, this amount per day will be 365 times that amount will be 18.4% in a year. However, this is not including the effect of compound interest that accumulates interest on interest, and that can really blow up. So just introducing some symbols, I use the subscript n for the length of compounding interval per year. So a quarter, so 1/4 is for a quarter, and n over 1/365 is for a daily, and n equals to 1/12 is monthly, and n equals 1/2 is semi-annually. All right, those are the key ones. I could do so many others, but those are the ones that we're going to focus on for this class. The inverse of n can be interpreted as the number of compounding periods per year, right? Because if you have a quarterly rate, that means it compounds 4 times in a year, so you just invert this. If it's a daily rate, it compounds 365 times in a year, so you invert this. Okay, so that's the relationship between n, a fraction of a year, and 1/n, which is the number of compounding periods. So some key rates that we need. So just as examples, the annual rate compounded daily is the stated daily rate on credit cards, APR 1. So I use the notation R1365. These are rates per year compounded every period. Because these do not match what I've underlined, these are stated rates. The annual rate compounded monthly is equal to the stated monthly rate, R1/12. This is for mortgage rates, okay, in the U.S. So if you have property in the U.S., you'll have a stated rate. You'll need to divide that by 12 to know what you are being charged interest every month. And the annual rate compounded quarterly is denoted like this. We would have to divide by 4 to work with dividends to pay to stockholders, because dividend payments are often quarterly. And finally, the annual rate compounded semi-annually is the stated semi-annual rate. Again, in each of these statements of the rate, the statement does not match the compounding frequency. They're all annual rates. So it's coupon rates on coupon bonds and yields to maturity on bonds in the U.S. are in stated in their stated semi-annual rates. So what you need to do when you get these rates is convert them immediately to use them. Otherwise you can't use them. So you convert this into an effective daily rate by immediately dividing it by the number of days, and that converts it to a daily rate. This one you can convert into an effective monthly rate from mortgage payments. So you just take it and you divide by 12. This subscript is just it's just down here. You don't do anything with it. It's just the total. It represents the rate. And for the quarterly rate, you convert it to the effective quarterly rate by taking it and dividing it by 4, the number of periods of compounding in the year. And finally, you convert a semi-annual rate to the effective semi-annual rate by dividing it by 2. Okay, so that's how you convert stated to effective rates. You just divide by how many periods of compounding in a year. You want to see, Justin, you want to see the whole page? You have these notes, but I'm just adding. You want to see the whole thing? Some part of a sentence is missing where in another page. Okay, so this is document 5.5, and you just can read it over. You can take a screenshot if you want to preserve what I've said. And what I want to do is then, these are all the rates I just described. And this is the general relationship here. If you want to convert from a stated rate to an effective rate, this is the formula. You just divide the stated rate by the number of compounding periods per year, and it's, you'll notice, it's the inverse of this number. So if it's daily, you divide by 365. Monthly, divide by 12. Semi-annual, divide by 2. And quarterly, divide by 4. So this is just reiterating what I say. I also refer to these rates as nominal rates. But I like the word nominal for other purposes, so I might not say that again. So I call these stated or nominal rates. Okay, so what next? That's the relationship between effective and stated rates. And then you have time to review this. Don't feel disparaged that I'm rushing. So I'm going to go to number 6. Whoops. Number 6. So these are just summary documents, okay? So what we've done so far, I've already discussed this. The notation, I discussed this relationship between effective rates and nominal or stated rates. They're just versions of simple interest rates. So that's one technique you need. Another one is to convert from effective to effective rate. And what I've done is shown you here those are all equivalent rates. These are effective periodic rates. And what I've done is said 2 semi-annual periods make a year. So 2 factors of compounding semi-annual period makes a year. 4 factors of accumulating quarterly rate makes a year. 12 factors of accumulating the monthly rate makes a year. 365 days of accumulation of the daily rate of the factor of the daily rate, 365 of them make 1 year. Okay, so those are all interrelated. It means I can convert an effective annual rate to any of these, and I also can convert any of these to the others using this relationship. These are equivalent rates. So just to illustrate what I'm talking about, okay, so this is let's say I had the effective monthly rate every period. I gotta make it bigger. Right, so in every period you have the effective monthly rate. So this is like a mortgage where if any outstanding balance on repaying money borrowed to buy property gets charged, you get the point, right? Every year or every period. So then 12 of those make 1 year. But let's say I wanted to convert to an equivalent rate over a different period. And you're going to see many examples of that. Let's say you wanted to convert between a quarterly rate and a monthly rate. Which rate is bigger, the quarterly rate or the monthly rate? The quarterly rate is smaller than the monthly rate. What did I just say? The monthly rate is smaller than the quarterly rate. And so there's actually 3 quarters in a month. So you can see that if you wanted to find the monthly rate from the quarterly rate, you could do it either using these exponents or these exponents. You can solve one from the other. So let me see if I can, before we go, you can read through these. I've discussed most of this material. These are just for you to review or have a record of. In document number 7, I go through some applications. I deal with bonds and I deal with mortgages. And let's see if we can do this, some of this before we go. So this is document 7. That's right, Jeffson, Samuel. Sorry, I was tapping on my pen. Didn't realize it was. I have an Apple Pencil. Okay, you ready? A mortgage is an example of an amortized loan where the principal is paid over time, not at the end of the loan period. So it means that the loan continues to accumulate interest even though you've paid off a portion. Banks often quote mortgages as annual interest compounded monthly, where interest is calculated or compounded every month. But they only state it in terms of simple interest over the year. The term of a mortgage are usually renegotiated during the term of the mortgage. For example, the interest of my 25-year mortgage will be negotiated 5 years after the initiation of the mortgage. So you've negotiated a 25-year mortgage to start with, let's say $100,000 mortgage at a rate of 7.4% per year compounded monthly. So first of all, that is a stated rate which needs to be converted to an effective rate, and that's done here. So this is done here. Just a note, to answer mortgage questions, since payments are monthly, we first have to convert the quoted or stated rate to the actual interest rate charged each month. That is, we need to calculate the effective monthly period rate. So now that we have that, we could store it like this in our calculator with store 1, but don't forget to multiply by 100 if you're going to use it in your annuity, as an annuity in using your TVM keys. So the first question is, what is the monthly payment on the above mortgage? So let's do that. And I've given you solutions for everything. I'm just not going to give you solutions for the last document. So what is the monthly payment on the above mortgage? So you need to, we've already done this, right? So it's $100,000 for 25 years. So first we have to identify payments are monthly. So convert everything, all the variables, to months. So that means that T is going to be 25 years times 12 months in a year. So that is going to be how many months? And then your rate that you have already is in monthly rate. And are we ready? We're going to present the formula now that the present value of the mortgage is $100,000, and that's equal to the payment that we're trying to sort out, so that's the cash flow, the initial cash flow, divided by the monthly rate. And this is the one that the calculator must solve. So that will give us the payment, and we've done this already, so we're good at this now, right? So N is 300. So 300 into N, and then recall 1 times 100 into interest, and then 100,000 is received, so this goes in as a positive to PV. Payment is what we want to compute eventually, and we're going to put 0 into FV. So we compute payment, and what do we get? So let's do this. So I'm going to take 0.074 and divide by 12, and that is going into store 1. Then I'm going to put 300 in N. Recall 1 times 100 goes into interest. 100,000 goes into the principal amount. 0 into FV. Any questions so far? Compute payment. So you will have to pay, on a mortgage like that, it would be $732.50. And I round it because payments are made in dollars and cents, right? Individuals don't make payments in fractions of a cent. So it would be $732.50. So the result is $732.50. So now the payments are always $732.50. That doesn't change. The interest rate is always 0.0061667, or 0.616667%. That doesn't change. What I'm going to do here is we're going to show the amortization of the loan so you can see this in action. Before we go, let's do a little bit of this and then I'll leave the rest to you. The loan begins, I'm going to make this even bigger. With a balance of $100,000 owed. What you need to do is take the interest rate and multiply the $100,000 by it to know what is the interest charged in the first month. In the first month, you're charged $616.67 interest. And this goes on, it adds on to your balance. Remember, we already calculated the monthly payment. The monthly payment was $732.50, which is not really a dent. It doesn't do much to reduce the principal. You're basically paying off the interest. It leaves a little bit to pay down the principal, but it's mostly an interest payment. It's mostly an interest payment. So let's see, how much does the principal drop after we've made our interest payment? You need to round these because these operations, these calculations are made, these payments are made in dollars and cents. So there is all that you get to reduce your balance. This is the principal reduction using the monthly payment. Your balance only went down $115. So in the first few years, you have in the first few years, most of your payments will go towards interest. And later, when you have less of a loan, when you've reduced it substantially, the interest payments will be lower. So you'll see when we take care of the next row, you'll see that happening right away. So I'm going to put this balance here, and then multiply it again by the interest rate. So you see that because the balance has gone down, the interest payment goes down. The monthly payment stays the same. That doesn't change. And so your reduction in your balance will improve. Okay, so you're going to reduce a little bit more each month, more than before. All right, so I'm going to leave you to finish the table and work with the materials I've given you. I want to show you one thing before we go, and that is the summary sheet that I created to summarize what has been taught. I'll send this to you. I didn't send it yet, but I will send it to you. Or maybe, no, I didn't send it yet. Number 12, because I think I only sent you up till number 10. So this, together with your formula sheet, is a really good takeaway for, oh, that's not it. That's not it. It's not number 12. So I have to give you the summary sheet. Okay, so I'll send it to you. I'm not sure where it is. So it's a summary of the technique of how to do this. But that was not it. Okay, so anybody have any questions? I'm going to send you the summary page and your assignment for the week. And what you're going to do with Taylor is work on all these exercises together. Okay, so I'll send that to you. And wish you a great afternoon and a great week. And if you need anything from me, please don't hesitate to contact me. I don't know if I gave you my phone number. Some students have it from last time, right? So this is my, I'm putting this on YouTube, but it doesn't matter. No one's gonna call me. So you can text me through WhatsApp. I guess you have to use +1. You know that, right? And you can contact me if you need to. If some students are still concerned about the statistics, in terms of statistics, if you the statistics course that we already took together, or you took it from me, if you are interested or you need a retest, please let the administrators know, and I'm open to that, of course. Okay? So have a good week. I know it's a lot, but it looks like some people get it, and I'm hoping they'll help the others. And Taylor's, there's always Taylor we can count on. So we survived our first weekend. Bon appetit. Enjoy your lunch. Bye, Natalie. Bye, Ironel. Samuel. Jefferson. Luxo. Alain. Harry Charles. Saver. Marcel. Anouk. Et Monsieur Sever. Jephté. Ernst Jean. Francette, cat forgets Francette. Very good. It's so nice to hear from you. Okay, so we'll see you next Friday. I know I need rest. How did you know, Jeffson? I'm exhausted. Bye-bye. See you next Friday. Thank you, Diego.
O Elisi Diego. It's blurry. Sorry, the screen was blurry. Ok, bye bye. A bientôt.